So, as I mentioned previously, we're going to just expand solving more complicated systems of equations. All right, we're going to do that with matrices today. We'll continue using Gaussian elimination, which is the method that we went over last week, and we will also expand it to what's called Gauss-Jordan elimination. All right, here's our definition of a matrix, which we have gone over before, so this shouldn't be anything too crazy. Just, of course, remember that these little subscript numbers here, the first number represents what row you are in, right? Rows are horizontal. And the second number represents what column you are in. Columns, of course, are vertical. All right, we say that the dimensions or the size of a matrix are the number of rows by the number of columns. All right, so we'll go over some very easy examples here, just giving the dimensions of a matrix. All right, this is obviously a 1 by 1 matrix because we just have one row and one column. All right, here this is a 1 by 3 matrix. Right, so this is a 1 by 1. This is a 1 by 3, right? Because we have one row and 1, 2, 3 columns. All right, this is going to be a 2 by 2 matrix because we have 1, 2 rows and 1, 2 columns. All right, this is going to be a 3 by 2 matrix because we have 1, 2, 3 rows and 1, 2 columns. All right, and this is going to be a 3 by 5 matrix because I have 1, 2, 3 rows and 1, 2, 3, 4, 5 columns. Okay, so we can actually use matrices to represent systems of equations. Okay, so if we have some system of equations given to us here, all right, then what we call the coefficient matrix is literally just all of the coefficients, which of course are the numbers in front of variables, right? So 1, -4, 3, that's where we get this row from. -1, 3, -1, which is where we get this row from. And 2, 0, -4, which is where we get this row. All right, the constant matrix is simply all of the constants that the equations are set equal to. All right, so that's why we have 5, -3, 6 right here. Now, when you stick the coefficient matrix and the constant matrix together with just some dotted or dashed lines, all right, that's what's called the augmented matrix. All right, so we literally go across our rows here, and every coefficient and or constant, right, we just simply put them in our matrix. And the dotted or dashed lines here essentially just represent our equal signs. All right? This is called an augmented matrix, and this is what we will use primarily when we do Gaussian and Gauss-Jordan elimination to solve systems of equations. All right, so it says write the augmented matrix for the system of linear equations. All right, so if I'm going to write this as an augmented matrix, all right, we will have 1, 3. There is no z term, so I put a 0. We have to do that. All right, put my dotted or dashed line for the equals, and then 0. All right, then my next equation. Now I don't have an x term, so that has to be a 0 for my coefficient. And then -1, 4, -2. All right, here my coefficient for my x term is 1. I don't have a y term, so that's 0. My coefficient for z is -5, and my constant is 0. All right, so this is my augmented matrix for this system. It then says, what is the dimension of the augmented matrix? Well, I have 1, 2, 3 rows, and I have 1, 2, 3, 4 columns. So this would be a 3 by 4 matrix. Pretty straightforward. All right, elementary row operations for matrices. These are the exact same things that we were allowed to do when we were actually writing out the full equations last week. All right, so we can do all the same things. We can interchange two rows. We can multiply one of the rows by a non-zero constant, and we can add a multiple of one row to another row. All right, so nothing changes as far as what we're allowed to do. Really, the only thing that writing a system in an augmented matrix helps us with is that we don't have to write down X, Y, and Z a bunch of times. Right? And when you have to do multiple iterations, that can save you some time, and it's often easier to just keep things organized. All right. So if we want to interchange the first and second rows, right? Remember, it is best to keep track of all of the things that you do so that I have an idea of what you're doing when you're performing row operations. All right. When we were just doing the equations, I called it E1, E2, E3. Same concept here, but now we aren't really talking about equations here. We're talking about rows of matrices. So it says to interchange the first two rows. So if this is row 1, this is row 2, and this is row 3, all right, well, if it wants us to interchange the first two, then this is row 2, so -1, 2, 0, 3. All right, row 1 becomes row 2, so 0, 1, 3, 4. All right, we don't change row 3 at all. It didn't tell us to do anything there. So I keep it 2, -3, 4, and 1. All right, so, and then of course, if we were continuing on, this would now become my new row 1. So when I write, how I'm manipulating my matrix in my next iteration, this is now considered row 1, this is row 2, and this is row 3. It gets too messy if you try to compound what you're doing with these matrices. All right, multiply the first row of the matrix by 1/2. All right, well, no big deal here. So all I have to do is 1/2 times row 1. So I would get 1, -2, 3, -1. And we don't do anything to rows 2 or 3, so we would just keep those the same. 1, 3, -3, 0, and 5, -2, 1, 2. So these are just very straightforward operations here. So add -2 times the first row of the original matrix to the third row. Okay. Now, when we're combining the first row and the third row, really we could have it replace either the first or the third row. In this case, we would probably want it to replace the third row. The reason why is because, remember, with Gaussian elimination, we want our leading number here to be a 1, and then we don't care what comes after it. And we want 0, 1, and then we don't care what comes after it. And then we want 0, 0, 1, right? So if I add -2 times row 1 to row 3, that's going to make this a 0 like I want. So I would just keep row 1 and row 2. So 1, 2, -4, 3, and 0, 3, -2, -1. Right, and here I want to do -2 row 1 plus row 3. Oops. All right, so Negative 2 times 1 is negative 2, plus 2 is 0. Negative 2 times 2 is negative 4, plus 1 is negative 3. Negative 2 times negative 4 is 8, plus 5 is 13. Negative 2 times 3 is negative 6, plus negative 2 is negative 8. So that's just some examples of how we apply those operations that we're allowed to with matrices. Okay, so let's solve this by using Gaussian elimination. So this is exactly what we were doing at the end of last week, right? Wednesday is when we were introduced to it, and then Thursday and Friday we practiced with it. So this is the exact same thing, except now we don't have to write out the equations every time. We can just write it as an augmented matrix. Right, so when I do that, I will have 1, negative 2, 3, and 9. All right, and negative 1, 3, 1, negative 2, and 2, negative 5, 5, and 17. Okay, so of course this is my row 1, row 2, and row 3. Remember, when we're using Gaussian elimination, we do have to use every row at least once, and we can't combine the same two rows more than one time, okay? Remember, for Gaussian elimination, I want this to be a 1, and I don't care what comes after it. All right, so my row 1 is fine. Right, so we have 1, negative 2, 3, and 9. All right, now I want my first entry here to be a 0. All right, now I want this to end up being a 1 eventually as well, but we don't worry. Sometimes we get lucky, and we're going to here. All right, but the only thing that we care about with our first iteration is that we get the first column how we want it. All right, and then when we do the next iteration, we'll get the second column how we want it. And then when we do the third iteration, we'll get the third column how we want it. All right, so don't try to do everything all at once. You'll really mess yourself up. So here, we can easily just say row 1 plus row 2. So 1 plus negative 1 gives us the 0 that we want. Negative 2 plus 3, luckily, gives us the 1 that we want. 3 plus 1 is 4. 9 plus negative 2 is 7. All right, now I want this to be a 0 as well. All right, so there's a couple of ways that we could do this. Probably the easiest looks like 2 times row 2. So 2 times row 2 plus row 3. Okay, now do remember here that we had to use row 3 because we hadn't used it yet. All right, and we could have either combined it with row 1 or row 2. Either one would have been fine here, but so here we're going to get negative 2 plus 2 gives me 0. Here we're going to get 6 plus negative 5 gives me 1. Here, 2 plus 5 gives us 7. All right, and negative 4 plus 17 gives us 13. All right, so now I have that first column how I want it. All right, now with the next column, all right, I want this. This doesn't matter, right? Anything after the 1 is fine. This has to be a 1, which it is. All right, and this has to be a 0, which it is not. So my first 2 rows are perfectly fine. So I can leave them. We have 1, negative 2, 3, 9, right, and 0, 1, 4, 7. All right, now I want this to be 0, 0. I could either say row 2 minus row 3, or just to make this positive, I'm going to go ahead and say row 3 minus row 2. So 0 minus 0, of course, is 0. 1 minus 1, also 0. 7 minus 4 is 3. And 13 minus 7 is 6. All right, now I want this to be a 1, and we could just kind of do a whole new step, but we don't really need to. We can just take this whole thing, since both of these are multiples of 3, right, and we could just multiply that by 1/3. So that means this is going to be a 1, and this is going to be a 2. Okay, well, now we have it in row echelon form. So now we can go ahead and do our backward substitution. Now, just because this is in matrix form, we do need to recall that this still represents 0x plus 0y plus 1z equals 2, right? So this tells me right away that z is equal to 2. Well, then I can jump up to this row, which represents y plus 4z equals 7, right? So I can say, okay, well, y plus 4 times z, which we know is 2, is equal to 7. 4 times 2 is 8. Subtract 8 from both sides. Y is equal to -1. Well, now that I know y and z, I can jump up to my first row here. Remember, this just represents x minus 2y plus 3z equals 9, right? So we know that x minus 2y, which is -1, plus 3z, which is 2, is equal to 9. Right, so this is positive 2 plus 6, so that's positive 8. So if I subtract 8 from both sides, x is equal to 1. All right, so my solution to this system is 1, -1, 2. That is my order triple, right? My x, my y, my z. So it works the exact same way as the systems we were doing last week, but now we just put them in matrix form. All right. Here we can go ahead and do another example. All right. If I were you, I would pause the video here, try this one on your own. If you are able to get all the way through it, great. Then you can just press play and check your answer. If you get stuck, then you can try to press play and see where you got stuck. Now, you do have to keep in mind that different people can do these different ways and still get to the correct answer. All right, there is no just one definite way to get the correct answer. So if you do it a little bit different than I do, that's okay. It'll just be a little bit more difficult for you to check where you made your mistake. All right. So if we go ahead and put this as an augmented matrix, all right, we're going to get 1, 3, 4, 7. All right, we're going to have 2, 7, 5, 10, and 3, 10, 4, 27. And of course, this is row 1, row 2, row 3. All right, so to do our next iteration, I want this to be a 1, and then everything after it doesn't matter. It already is. So we can leave row 1 as it is. I want this to be a 0. All right, so I'm going to say row 2 minus 2 times row 1. So 2 minus 2 gives me the 0 that I want. All right, 7 minus 6 gives me a nice 1. All right, 5 minus 8 is -3. And 10 minus 14 is -4. I also want this to be a 0. All right, so I'm going to go ahead and say R3 minus 3 times R1. All right, so here we're going to get 3 minus 3 gives me that 0 that I want. All right, 10 minus 9 gives me a 1. 4 minus 12 is negative 8. And 27 minus 21 is 6. All right, so my first time through, I got my first column how I wanted it. All right, now we go ahead and focus on the second column. I want this to be a 1 and everything after it doesn't matter. I want this to be a 0, 1. Everything after it doesn't matter. So my row 1 and row 2s are perfectly fine. So 1, 3, 4, 7. All right, and 0, 1, negative 3, negative 4. All right, here I want this to be a 0. So here I can just say row 2 minus row 3. So 0 minus 0 is 0. 1 minus 1 is 0. Negative 3 minus negative 8 is 5. And negative 4 minus 6 is negative 10. All right, so of course, again, if you wanted to here, since these are obviously both divisible by 5, and I want this to be a 1, I could just multiply that whole row by 1/5. And doing that will make this a 1 and this a negative 2. So 1 and negative 2. And if you take a few more steps to get there, that's perfectly fine. It's no big deal. You don't have to do it in the exact same amount of steps that I do. All right, so of course we need to remember that this is 0x plus 0y plus z is equal to negative 2. So this tells me that z is equal to negative 2. All right, then I can jump up here and say, okay, well, y minus 3 times z, which I know is negative 2, is equal to negative 4. So that's positive 6. Subtract 6 from both sides. Y is equal to negative 10. Then I can jump up to my first row here and plug in my y and my z and solve for x. So x plus 3 times y, which is negative 10, plus 4 times z, which is negative 2, is equal to 7. All right, so here we have negative 30 plus negative 8, so that's negative 38. So we add 38 to both sides, and we get x is equal to 45. All right, so my order triple, my solution for this system of equations is 45, negative 10, and negative 2. And we are done. Like I said, there's a lot more ways to get to this final solution than what I did. So if you were able to do that, fantastic. All right, so now we're going to talk about row echelon form, which we essentially already did. All right, but this is just a very formal definition. All right, so a matrix is in row echelon form, has the following properties. All right, any rows consisting entirely of zeros occur at the bottom of the matrix. All right, so you are allowed to have rows that are all zeros, they just have to be at the bottom. For each row that does not consist entirely of zeros, the first non-zero entry is a 1, right? And for two successive non-zero rows, the leading one in the higher row is farther to the left than the leading one in the lower row, right? So if we kind of look at this back here, right? So whenever we have non-zero rows, right, the higher row, the one needs to be further to the left, right? So this one is further to the left than this one, and this one is further to the left than this one, okay? Then it also goes a little bit further here, right? A matrix in row echelon form is in reduced row echelon form when every column that has a leading 1 has zeros in every position above and below its leading 1. So in order to be in reduced row echelon form, right, this would have to be a 0, and these two would have to be zeros. All right. Over here, you're allowed to have other numbers. right? But that actually makes our solutions really easy, so we'll talk about that a little bit more. All right, so first we just want to kind of check whether things are in row echelon form or not, and if they are in row echelon form, see if they're in reduced row echelon form. Okay, so here, right, um, every non-zero entry, the first one is a 1, which is what we want, and higher rows, the ones are further to the left, so we're good there. So this is in row echelon form. It's not in reduced row echelon form, all right, because these two entries right here are not zeros. Right? If both of these were zeros, then we would be in reduced row echelon form. All right, and this one is very similar. In fact, it's the exact same one. So that was just obviously copied over. So obviously this is in row echelon form as well. All right, so here, bottom row, my first non-zero entry is a 1. That's fine. Same thing here, and it's further to the left, and it's a higher row. Same thing here, it's further to the left, and it's a higher row. Up here, my first non-zero entry is a 1, and it's further to the left. It doesn't matter that it's 2 spots further to the left. It just matters that it is further to the left. So yes, this would also be row echelon form. All right, down here we have all zeros, but it's at the bottom. That's fine. All right, here I have a 1, a 1, a 1. All right, and every entry above and below that 1 is a 0. All right, there isn't a leading 1 here, so these don't have to be zeros. Right, so not only is this row echelon form, this is reduced row echelon form. All right, here, my first non-zero entry in this middle row is actually a 2, not a 1. So it's neither. It's not in row echelon form, and if it's not in row echelon form, it certainly can't be in reduced row echelon form. All right, here, I have an all 0 row, but it's in the bottom, so that's fine. All right, here, my first non-zero entry in each of these 2 rows are 1s. That's fine. All right, and wherever I do have a leading 1, namely here and here, every entry above and below that in the same columns are all zeros. So this is reduced row echelon form. Okay, so we've already talked about this Gaussian elimination with back substitution. All right, so I'm not really going to take the time to read over this again. All right, but you've definitely seen it multiple times. This is how I've solved every one so far. So we just get it in row echelon form and we're good. All right, do be mindful here, if in the elimination process you obtain a row with zeros except for the last entry, then you can conclude that the system has no solutions, right? If we get one of those contradictions, right? If we get 0 equals 3 or 0 equals -5, that's how we get the no solutions. And we looked at no solutions and infinite solution problems last Wednesday. All right, so here, all right, we have, now we have 4 equations with 4 variables, right? X, Y, Z, and W. All right, now I know that W comes before X, Y, and Z in the alphabet, but they always put it after Z when it comes to systems of equations. So do be mindful of that. All right, so we'll go ahead and take a look at one. These are a little bit more tricky, and they didn't have any with this many equations and this many variables on Delta Math, so you won't see any of these in your homework. We'll probably put one of these on your test on Friday, but it'll probably be a bonus question. Okay, so don't fret over it too much. All right, so we're going to have row 1, row 2, row 3, and row 4. So we're going to have 0, 1, 1, negative 2, negative 3, all right, and we're going to have 1, 2, negative 1, 0, 2, and 2, 4, 1, negative 3, negative 2, and 1, negative 4, negative 7, negative 1, negative 19. Okay, so I'm just doing the same process as far as getting it in row echelon form. Eventually I'll show you getting one in reduced row echelon form and how that can help us. All right, but for now we'll just keep doing the same thing that we were doing before. All right, so here I want this to be a 1 and I want this to be a 0, 1. So I'm just going to go ahead and switch these two. All right, I'm going to go ahead and say, okay, well, row 2 can become my new row 1. So I have 1, 2, negative 1, 0, 2. All right, and then I will have my row 1 will be my new row 2. So 0, 1, 1, negative 2, negative 3. Here I want this to be a 0. So I am going to go ahead and say negative 2 R2 plus R3, right? So I'm going to multiply this row by negative 2, then add it to this row. So negative 2 plus 2 gives me 0. Negative 4 plus 4 gives me 0. That worked out nicely. All right, 2 plus 1 is a 3. 0 plus negative 3 is negative 3. And negative 4 plus negative 2 is negative 6. All right, now remember, I am going to want this to be 0, 0, 1. And since these are all nice multiples of 3, I can kind of just take this and multiply it by 1/3. Just for ease sake, I'll just divide it by 3. All right, so this will be 1, negative 1, negative 2. All right, so 1, negative 1, negative 2. I also want this to be a 0. All right, so I'm just going to go ahead and say R2 minus R4. And there's a few ways that you can do these. Remember I said there's a bunch of different ways. So if you saw something else first, like something else comes to your mind, it's okay. As long as it gets us to where we want to go, it's perfectly fine. All right, so here I'm going to have 1 minus 1, gives me the 0 that I want. 2 minus negative 4 will give me a 6. All right. Negative 1 minus negative 7, that will give me a 6 also. 0 minus negative 1 is a 1. And 2 minus negative 19 is 21. All right, so, sometimes we like to multiply these by the reciprocal of this to get this to be a 1 or whatever. Of course, eventually we're going to want this to be a 0 and this to be a 0. All right, so it's really not a huge deal there. All right, so we're not, and if we did try to multiply this whole thing by 1/6, we would get messy fractions here. So don't do that. It's just going to make it much harder for you in the future if you do. All right, so my row 1 is fine. My row 2 is fine. And actually my row 3 is fine. All right, because I want 1, a bunch of stuff, 0, 1, some stuff, 0, 0, 1, some stuff. All right, so these are all fine. So 1, 2, negative 1, 0, 2, right, and 0, 1, 1, negative 2, negative 3, and 0, 0, 1, negative 1, negative 2. All right. Now I want this to be a 0, which it is. I want this to be a 0 as well. All right. Of course, I want this to be a 0, but remember, we can really only focus on one column at a time. Okay. Now, in order to get this to be a 0 without changing this, the only other row that I can combine it with is this one, right? Because any multiple of 0 added to any multiple of 0 will still keep that a 0, which we don't want that to change, right? And then I can multiply this by negative 6 and add it here to get my 0, all right? So I'm going to say negative 6 row 2 plus row 4. So 0 plus 0 is still 0 that I want. Negative 6 plus 6 is the 0 that I want. Negative 6 plus 6 again is the 0 that I want. All right. And negative, well, this will be positive 12 plus 1 will be 13. All right. And 18 plus 21 is 39. All right, really, I can just multiply this whole thing by 1 over 13. All right, and when I go ahead and do that, I will get 1 here and 3 here. So 1 and 3. Well, now this is in row echelon form. All right, so I can go ahead and use our backward substitution. Okay, so this tells me that W is equal to 3. Then I can jump up here, and that will say 1z minus W, which is 3, is equal to negative 2. So add 3 to both sides. Z is equal to 1. All right, so now I can come up here, and I can say y plus z, which is 1, minus 2w, which is 3, is equal to negative 3. All right, so this is negative 6. 1 minus 6 is negative 5. So if I add 5 to both sides, y is equal to 2. Now I can jump up to my top equation here. All right, and that tells me that x plus 2 times y, which is 2, minus z, which is 1, all right, plus 0w, which is fine, is equal to 2. So here 4 minus 1 is 3. So if I subtract 3 from both sides, x is equal to negative 1. So this is actually in ordered quadruple. Remember, we say x, y, z, w. So negative 1, 2, 1, 3. All right, and that's as hard of one as you will ever see. And like I said, on your test, that'll probably just be a bonus question. All right. Since it's just going to be a bonus question and they take so long, I'm going to go ahead and skip this problem. I can do it tomorrow if you guys would like. And here's a bunch more of them. All right. So I'm going to call it a day here for today, and let you guys just kind of do the practice that I have up on Delta Math. All right. And then tomorrow I'll go over another one of these, and I'll get into Gauss-Jordan elimination, which uses reduced row echelon form matrices instead of just row echelon form. And really all that's going to do is eliminate the need for us to use backward substitution. All right, but I think today that's going to be a good place to stop. So I will end it there.